Okay, so we immediately see that the magnitude of r prime of t is pi over 2 square root of t times the square root of 4 sine squared of pi square root of t, which I won't write out in detail. Just leave a set of empty parentheses for the pi square root of t, because we know what goes there, right? Okay? How do you get a handle on how this behaves in a given cycle? Now, we already saw that this implies a decreasing factor out here, right? So overall, every cycle of this thing, every time t changes by enough to change this by 2 pi, right? Which means t changes by 4. Of course, we drew a graph and saw how that works, okay? Every time that happens, we do a cycle of an ellipse with an axis of 2 in the x direction, 3 in the y direction, right? So we're going around this ellipse, but more and more slowly. Now, within that cycle, the speed changes by this factor, right?
Where did you get that magnitude?
Just take, and of course there's an I here and a J here that I left off, okay? Just dot this with itself, or just take, here's the x component, here's the y component.
Oh, so you don't have to do anything with the first factor?
Technically speaking,
No, it factors out, because you're going to take the square root of the sum of the squares of the x and the y components, right?
Okay, so the first factor is not...
This is going to be squared, but under the square roots, we just pull it out and there it is.
yeah, because essentially we can put it back in. Whenever we go through squaring it all, we'll have 2 squared versions of that,
Yeah.
and then we can drag them out because it's a like product for both. It's
Yeah.
component for both of those.
And of course, if you write it out in detail, then if you know this, you'll see where that comes from, okay? But that's where it comes from, okay? Now, the thing I just wanted to show you here is we talked about how speed changes during the cycle. Had questions on whether it maximizes at the same part of the cycle or not, okay? And where does it maximize? Now, intuitively, it's kind of obvious it's going to maximize either when it hits the x-axis or the y-axis. And you can think about why that's intuitive. I don't want to spell it out for you, but I mean, later, you know, after you've thought about it and still don't understand, we'll talk about it, right? But what I wanted to say is this is pi over 2 square root of t. When you have this, you notice that you could take 4 of these and put together with this and get 1, right? 4 times the sine squared plus 4 times the cosine squared is just 4, in other words, okay? Pythagorean identity, so this is 4 plus 5 cosine squared, and now I'll put the pi square root of t in there, okay? So now, what happens on the ellipse? Here's your ellipse. See if I can draw a half decent ellipse. If I try really hard, maybe. That's not too bad. Okay. So here's your ellipse. Here's your r of t function. And here's your r prime, which of course is your velocity function, right? And you've got an acceleration function that's a derivative of this, right? Now right here, is this thing speeding up or slowing down?
Slowing down.
Maybe. But maybe since the ellipse is getting more and more elongated, it's speeding up, okay? So you want to think about that. And, you know, just whatever it takes. But you can see here that this is going to be, what, increasing when the cosine, well, it's going to hit its maximum when the cosine is 1, right? Because it's going to be the square root of 9, okay? Or when the cosine is negative 1, right? Well, where is the cosine 1 and where is it negative 1? Well, okay, the cosine, okay, if the cosine is 1, then the sine is 0, right? Now, if the cosine is 1 and the sine is 0, then where are you on the R of t function? Let's go ahead and write the R of t function. And it's just 2 times the cosine of this thing times I, plus 3 times the sine times j, right? Where are you? Well, if the cosine is 1, your velocity is a maximum, and if the cosine is 1, you're at 2, 0. So that's the thing I wanted to, first of all, the idea that when you see sine squareds and cosine squareds, you try to combine them so you can use a Pythagorean identity, sine squared plus cosine squared of the same argument is 1. So we do this, and now we have an expression that we can see, right? We could even graph this. It's useful to graph let's say y equals 4 plus 5 cosine squared theta versus theta. Okay, so you have an axis here where y equals 4. The cosine of 0 is 1, so you'll be up here at 9. Of course, I didn't leave myself enough room. I should have drawn that a little lower. So the scale's not going to be great, but you got, and things are bunched up. Y equals 9 here, and y equals -1 here. Your graph is going to start up here. It's going to go down to the negative. It's going to go back to the positive. It's going to go down to the negative. And you know, if time extends in the negative direction, which it might, depending where you start your clock, okay, you have this.
How does it go to -1?
Well, because, oh, it's cosine squared, right? So, yeah, the graph is wrong. It's going to be like this. A little careless of me, but get used to it. Okay. So, right here's our graph of 5 plus cosine squared theta. The graph I drew would have been 4 plus 5 cosine theta. And it's useful to see how this graph is related to this one too. You want to maybe think through that. But there it is. Okay? So we see that when theta is 0, pi, 2 pi, right? And of course that means here and here. And of course theta is pi square root of t. But this is where it's going to be on the ellipse. Now, so as it slows down on the ellipse, you know, it takes longer and longer to get around the ellipse, but it's going to be going faster here than it is here, faster here than it is here, faster here. Okay? So that's just some useful manipulations that are totally within your capacity. Okay? So you can kind of take a lesson on that. Now most of the analysis that you'll be doing doesn't necessarily go that deep or isn't necessarily that tricky, but sometimes it is, and you got to be aware of tricks. It's not really a trick, it's something that you, with experience, you just see immediately when you look at this expression. Okay?